Exactly. I'm solid-state physicist, mostly work on solar energy conversion to electricity by designing new material and new devices for this purpose. I'm professor of the Ben Gurion University of the Negev. You know that Israel is a very small country, and 60% of the country is occupied by the desert, the Negev. And even by the name of our university, you can see that we sit, and especially our faculty, is really, you can see a photo of our campus. It's not in the city. The nearest city is Beersheba, but we are in, the campus is called Sde Baker. It's in the middle of the desert. And our faculty is called Jacob Blaustein Institute for Desert Research. It means it's a 3 institutes, all deals with the development of technology to live in the desert. The first is Water Institute. You know that Israel, Middle East in general, and our world in general has a big problem with the sweet water. And today, our 70% of the sweet water of Israel is desalination water. And the technology is the osmosis versus osmosis is developed in the Ben Gurion University. Another institute is agriculture, agrochemistry, all kind of agricultural problem. And our institute is called Institute of Energy and Environment. And the department is called Department of Solar Energy and Environmental Physics. And for many, many years, my interest in polyhedrogeometry, symmetry, and history of polyhedrogeometry, long history, comes from the fact that I was interested in studying using Buckminster-Fullerene molecule, carbon-60 molecules, a beautiful molecule in the shape of truncated icosahedron. And Michael, just before me, mentioned twice, I think, or 3 times Buckminster-Fuller. And you can see arrows in opposite directions between 2 icons, one by Leonardo and one by Dürer, showing that in our laboratory we work in opposite directions. We use Fullerene molecules to create materials and devices to convert solar energy to electricity. And at the same time, we are trying to synthesize these nanomaterials by sunlight. But today, I will tell about something different, which my story of learning of Roman Cosmatesque started in October of 2019, when I came to Rome for sabbatical. And I came mostly to study perovskite solar cells and perovskite materials for photovoltaic, but I also continue to learn, and I succeed, for example, to enter to Vatican Library and see in my hands this manuscript by Piero della Francesca with the first drawing of truncated icosahedron. But then one of my colleagues, Andrea Reale, from University of Tor Vergata, where I worked, told me that my father is interested in, his physicist is interested in symmetry. May you talk to him? And he invited me, my son, and my wife to a lunch. Every week he say, yeah, let's meet in this lunch this Sunday. But then he say me, no, my father continue to, he needs some week to prepare. I was start to afraid about it. And eventually we come to this beautiful city near Rome. It's called Tusculum, it's an ancient city. And I met Ormando Reale, and I recognized that he's a legendary nuclear physicist. For example, in this photo, you can see the conference, the young Orlando is sitting, and the 2 guys sitting in the first row is Schrödinger and Heisenberg. And he told me, we had a beautiful discussion about it. And he told me about, when he asked me a question, when you go to church, where you look for, even the museum, you need to look underfoot. And then he told me about Cosmatesque and presented me a small brochure. Actually, it's a reprinted brochure by some German mathematician in which it was shown that Cosmatesque has all kind of two-dimensional ornament groups with all kind of symmetry operations on a plane. So I started to be interested in working in churches in Rome and learn about Cosmatesque. Now for myself, I'm an expert. I can find it everywhere, and Cosmatesque style. And my aim today is to share my admiration about this. I will not talk a lot about symmetry groups and whatever, because I think it's obvious for this. I will talk about something else. So what is Cosmatesque? Is a style of geometric decorative inlay stonework, typical of the architecture of medieval Italy. Actually, it was disappeared in Renaissance time, and especially of Rome and its surroundings. It was used most extensive for the decoration of church floors, but not only, and also walls, pulpits, and bishop thrones. The name derives from the family name, Cosmati, the leading family workshop of craftsmen in Rome, who created such beautiful geometrical marble decoration during 20th and 14th centuries. And I told you, by some reason, if somebody is interested, we can discuss it, why it's happened. In a Renaissance time, it was disappeared. Cosmati floors are made from variously shaped and size of stone, a property quite different from Opus Tessalano mosaics, in which the patterns are made from small units, which are all the same size and shape. And all these, of course, piece of materials came from ancient Rome. It was a lot of such materials in medieval time in Rome. And the stone used by Cosmati artists was often salvaged materials. It comes from ruin of ancient Rome, what I told you. Yes, it's a different versions about the history. According to one version, the source of the original art of Cosmati should be sought in the East, in Byzantium, and even in the art of Islam. According to us, it was exclusively in Italy, a country rich in marble of various colors, which the ancient Romans successfully used in their art of cladding. The place where the marbles of Cosmati family first shows themselves, it was near to Rome, not in Rome. It's called Benedictine Monastery of Monte Cassino. And I would like just to mention the following main Cosmati. The first known was Lorenzo, and you can see the time of their walking. There is a street, Via dei Cosmati, in modern Rome. Let's go together through Roman churches. And the first, I would suggest you to go with me to Basilica on San Clemente. In Italian, it's Basilica di San Clemente el Laterano. This is a unique complex because it's not just one building, it's three buildings, all up to other. The present basilica, you enter and to see this beautiful Cosmatesque, it's built in 20th century. Beneath the present basilica, it's a building of 8th century basilica that had been converted out of home of Roman noblemen, part of which had in the 1st century briefly served as an early church. But even beneath it, there is a home of Roman noblemen, and it's 64 AD. So what you can see here, this is the upper church. This, if you go back, you can see this is the church beneath it. And when you go to the deep church, you can see also, it's out of topic of my talk, but it's a beautiful example of photosynthesis. It's a lot of water there, but you see this only where you have a local light, you can see this kind of green life. Yes, the next we go to the main Basilica of Rome. It's Basilica of San Mary Major, or Basilica di Santa Maria Maggiore, and it's starting in 13th century. And you can see beautiful, symmetrical, and some kind of complicated Cosmatesque. And first of all, it's Magen David, we say in Hebrew, it's David shield, and it's a lot of symbolics. Our conference is called Symmetry, Structure, and Information. So they want to share with us by colors, by shapes, by structures, information. And they talk to the guy who came in medieval time and look on it. And you can see these beautiful different ring. Yesterday, somebody already mentioned this knot. And if you go to Don't Theory, you can see this Borromeo rings and even more complicated. I think that the Cosmatesque is a beautiful example of art and science connection. We can teach even on university levels. We can teach a lot of science using the examples of Cosmatesque. Near to this, you can see this the tomb of one of the Roman architectural giants, Bernini, architecture and sculptural, one of the main builder of Rome. And now you can see this octahedron structure, and inside a beautiful rhombal structure with you can. It's a 2 dimensions, but you feel 3 dimensions, yes. So, and this is another example. It's called it's an example of rhomboid tiling, and in geometry, the rhomboid tiling also known as reversible cubes, and you can see cubes, a tesselination of identical rhombs on the Euclidean place. Each rhomb has 2 60 degrees and 2 80 degrees angles. Beautiful game with this rhombal tiling was done by Maurice Cornelis Escher, and all mathematician and crystallographer like him very much. I like this. I like Istvan Orr's examples, and this you can see perspective, platonic solid, his way, and this is a library 3. Homage to Dürer, and this one. I knew Istvan from many years, but not personally. And I remember beautiful visit with Danish to his in Budapest to his. And this is another homage to Jan van Eyck. And if you have time, we can talk about this Jan van Eyck picture as another topic of the lecture. So we go to other church in the Santa Maria in Trastevere, and you can see also it's a lot of Cosmatesque. But what is interesting for us, it's 2 examples, and I would say that 1 second. Yes, we can see the fractal. We can see the Sierpinski Triangle, named after Polish mathematician Wacław Sierpinski, who was active and studied this in the actually in the 20th century. And then you remember that I'm talking about pre-Renaissance era, yes? And just to give a definition for fractal is a set that has property of self-similarity, an object that exactly and approximately coincides with a part of itself. That is, a whole has the same shape as one or more parts. In mathematics, fractal are sets of points in Euclidean space that have a fractional metric dimensions. And I will also try to simply explain how it's possible, how the dimensions can be fractional. So, but what it is, you need to start with a triangle, and you can just take one triangle from the middle one, and then repeat it many times. Actually, infinite number of times you can get Sierpinski triangle. Also, I will try to put your attention, I will mention it in the end of my lecture, that it's a combination of white and black. It's white and blue in this case, but let's see if white and black, we can think about anti-symmetry. I will mention it. It's very important for, and color symmetry. Yesterday, Danish mentioned it in one of his comments. Yes, so this is a Sierpinski triangle, a beautiful fractal structure. And then now about dimensions. It's very simple. If you think about a square, and if you make 2 times size of a square, you can get 4 squares. And you can do it 3 times, you can get 9 squares. The same you do with triangles, yes? So if it's a cube, you can have 2 times, you have 8 cubes, and you can do it 3 times, you can get 27 cubes, yes? And then you introduce an idea of dimensions. And this is called, we understand, that cube and has dimensions of 3, square has dimensions of 2, and triangles, and line segment has dimension of 1. But what about Sierpinski triangle? If you do it 2 times, you can get 1 from 3. So your dimensions will be fractional, 1.585. So in Rome, you can also, I indeed enjoy fractal broccoli. It's a Romanesque broccoli. It's a beautiful example of fractal structure. So now we go to other Basilica, and you see 2 different structures, which both are very interesting. It's Mobius Strip, and the structure will be called Seed of Life. So if we talk about Mobius Strip again, it's possible to talk because this is an example of different space, and it has different physics. Actually, this space has different physics. We can show beautiful experiments about it. I will just show one Escher very beautiful explanation. One, it has only one surface, and also mentioned in Roman mosaic, we can see Mobius Strip much before medieval time. Yeah, but my interest was a long time ago. I wrote a paper together with a brilliant Chinese theoretical chemist from Taiwan. Actually, he's originally from MIT, about this kind of Chinese guardian lines, which put the lines of something which is similar to Fullerene or Fullerene duals. And one of these, it was shown that this is a 3-dimensional subject, 3-dimensional example of flower of light or seed of light. And actually we show that this contradicts to Euler's theorem, because all of these beautiful creations contradicts to Euler's theorem, because these Chinese sculptures, they didn't build entire sphere, they built only part of it. So you can see also Leonardo drawing of this flower of light in Jerusalem, in Israel Museum. You can see the beautiful mosaic from Herodion, from the Herodes palace, and it's a lot of other examples we have in Israel of this stuff. Yes. So another some connection with Israel, it's Solomon pillars, and you see how beautiful all this is. And again, please put your attention not only on structures, not only on shade, but also on color. It's a combination of different color, yes? And also, let's think about only white and black, yeah? So we can come to idea of anti-symmetry. Yesterday, we discussed symmetry, asymmetry, dissymmetry, but for physics, it's a very powerful idea of anti-symmetry, when your symmetry operation not only made a symmetry operation, but also change color from white to black. And this is only, of course, a special case of color symmetry, which is very, very important for real crystal physics and many other parts of science. And yesterday, Danish mentioned it. So if you, of course, in Cosmatesque, you can talk a lot of, I just put some examples of symmetry rotations of all known 1, 2, 3, 4, 6, or other forbidden orders of rotational symmetry. And if you think about anti-symmetrical axes, when you also rotate tetrahedron in my case, and they change the color from white to light, from white to black. And then you come to the problem, if you have a third order of symmetry rotation, because from the second order, 4th order, 6th order, no problem. You change from white to black tetrahedron or any other, and then go back. But if you do it in the 3rd order, let's say that you start with tetrahedron A in this. Can you see my mouse? maybe not one second, I can change it 1 second.
We can see
Yes,
your
we
pointer.
see, we see. Yeah.
Yeah, okay. Let's say that this triangle will be white, and then triangle B should be black, and then triangle C will be white, and then triangle A should be black. So if you do it many times, you see that all triangles ABC has no color, contrary to what's happened with orders of magnitude. Yeah, I also show some the simplest example of anti-symmetry translation is a chess field, and this actually chess is done by from the it's created as a model created on the basis of drawing Leonardo to the book of Luca Pacioli about the chess. And this photo I made in a city of Luca Pacioli, Piero Francesco, in a museum of Piero Francesco. So yeah, then Escher did this fantasy for changing white to black in day and night. Yes. So, yeah, I told you that in Renaissance time, the art of Cosmatesque was disappearing, but instead of it, starting with Giotto, you can see Cosmatesque on the painting. And yesterday, Carol showed us a beautiful Renaissance painting showing Eastern carpets, and here you see the Cosmatesque mosaics on the painting. Yeah, I will show you two examples, Giotto and Piero Lorenzetti. So yes, I have no conclusions. Again, my aim was just to show you some admiration of these beautiful examples and ask a question. I think it's open question. Why they do it? What's the message they wanted to tell us? Something I decided not to include in my talk. It was a Cosmatesque in Westminster Abbey. You know that the Cosmati was invited to London, and they made a beautiful Cosmati floor, and not only floor, some tombs in the Westminster Abbey. And it was only one example. They wrote something, and they wrote a message about the end of our universe, when it should happen, in their opinion. But I will not talk about it. Let's talk about it later. Thank you very much for your attention.
Thank you very much, Eugene. It was a great lecture, and you really linked art and science. So we have time for discussion. Please indicate if you have questions. I just would like to mention that you refer to Jürgen Misfeld's paper about the wallpaper group in this art. Am I correct? And what is interesting that I noticed that he is from Hanover, I guess from the Department of Mathematics, Hanover University. So may I share with you and others a very interesting fact that Hanover University was one of the center of researching of mosaic, we would say tiling and tessellation. Heinrich Heesch, or honorary member, but unfortunately passed away shortly after the first Congress. So Heinrich Heesch was the father of that group. He published many, at least 3 books about tiling. He used Parkettierung, so the parquets, the German word. But what is interesting to you that M.C. Escher, interesting to Eugene, but maybe from other people, that M.C. Escher, half-brother, was a geologist. And because Escher explained to his half-brother that he would like to make mosaics, his half-brother made a list of interesting papers which he should study. And Heinrich Heesch paper and George Poya's paper from Zeichen für Crystallography was among the papers which was George Escher suggested to M.C. Escher to study. So interestingly, there is some maybe historic link, at least as inspiration. In fact, Escher stated that he studied, but especially George Poya, Analogie der Crystallography, this was an interesting paper because he had representation all of the 17 wallpapers. So thank you very much. Questions, please. Dmitry.
Genia, I'm very impressed with your report. Very, very impressive. And I found in your report the illustration for my next report. This about Jan van Eyck. Can you show me a picture of Jan
Okay,
van
I will try. I need to do sharing again if Danish allowed me to do it.
Yes, of course, we have time. We have 3 minutes.
Then we will go to
example of using composition Mizanabim.
oh, sorry.
Fractal.
Fractals, yes.
Fractal.
Yeah, I remember. I remember. 1 second. If you do this way, sorry for this. It was the wrong way to do.
Mizanabim
Yes.
is formal technique for placing a copy of an image within itself. A copy.
Yes.
Yes. This great technique, and I found the picture. If you see triangle.
No, Dima.
It is very difficult to see
Very
via the
difficult.
camera.
Yeah, you just.
Triangle. And maybe this picture. For
Okay,
your,
Yeah,
better. Yes.
exactly. Yeah.
this there are. Oh yes.
No, we go to anti-symmetry.
Archetypes for periodic table. This is my next report. I
Okay.
will show that it is a pattern for periodic table.
Yes.
And
Okay.
I remark that pattern with triangles consists from square of triangles, little triangles. Big triangles is a square of little triangles. You understand me? Or
Yeah,
not?
yeah.
More or
Yeah.
less, yes.
More or less, yes. We can discuss it personally.
We can discuss it later because
I
we
would
have
be
a spare
happy
time
to
right
discuss
now.
all this.
Yes, and this is
Dima,
But-
время очень короткое. So, коротко, please. What is the question, please?
No, it was a comment.
Okay. Okay.
It was
is
a comment that.
Okay.
Yeah.
Okay.
I'm very impressed.
Okay. We should keep time. So thank much. We will have some time for discussion later. So don't worry. Be happy. I again would like to thank Eugene.
I have a
this
question,
wonderful-
Dennis.
Very
Yeah,
please.
we are.
I raised my hand.
Okay. Yes,
Okay.
please. But the time is
Um,
over, and I should keep the time, please.
Okay.
Very briefly.
This is just to ask, thank you, Eugene, for your presentation. Would you be so kind to show us one of the slides in Santa Maria Maggiore's church? Because there is a thing that I really want to catch.
Good. I will do it now in a correct manner, not in a.
Okay.
I think it was the beginning. Yes. Which one? This one?
No,
This was
before
a-
that. Before.
Before that? Yes. Just a second.
Before. Around
this one.
before.
No, this is the first
The-
in Santa Maria Maggiore.
Maybe the previous. Can you go to the previous? You have shown something that is one of my research motives, and I would like to trace it, but I'm not sure where it is.
Okay. So
Can you
I-
please go to after Jan van Eyck? Jan van Eyck.
after that, okay.
After
okay,
that,
okay. Yes, this one. This one.
the next one, the next.
The next is all about Sierpinski Triangle.
Okay,
So,
okay.
I can send you, Vera, let's do the following. I will send
Okay.
you the PDF file and then we can discuss about it.
Okay, thank you. Excuse
Thank
me,
you.
just one small suggestion. I will very much be interested in attending a Symmetry Congress in Israel. Sorry, I don't know how to say the name of your university. New
It's
Year,
Ben-Gurion University. Yeah, we already
Yes.
miss it.
but because I really would like to know Zvi Hecker's architecture
Okay.
in local.
So
I'm
you
very
don't
interested
need,
in him.
if you come to Israel, and maybe Michael also can do it, but I promise you to take you by car to all
Oh,
architecture. So
thank you very
and
much.
also, yeah.
Thank you.
Thank you.